Okay, well, let's go ahead and get started. Welcome to Networking 101. My name is Rhonda Grimm. I work for PerfTech, and we make the island router. With that, I will get going. Basically, this course is designed for you understand some of the elements, you're not quite sure how they fit all together, and we're just going to cover some of the basic concepts and get going. So let's start with how does data really move around the network and the internet, for that matter? How does everything get to where it's going? So computer networks are a lot like the postal system. There's this very loose analogy that both look for the most efficient route to get where they're going, where to deliver their package. So, for example, say you've got Alice, and she wants to send a birthday card to her friend Bob from college. And Alice is in the UK and Bob's in New York. So she wants to put this birthday card into an envelope. It's puts the sender's address on there and then address it to Bob. So this is the complete path taken by Alice to get her birthday card to her buddy Bob. So she goes to the mailbox, she puts the card in the envelope, she addresses it, she takes it to mailbox, the post person carries it to the nearest post office. That card goes by train to an office in London, and in London it gets on a plane and it heads to New York. Everything arrives in New York City at their post office. Mail carrier takes it and delivers it to the building that Bob works in, and the receptionist delivers it to Bob. So it's great. Everybody does what they need to do along the way. The post person in the UK has no idea how to get it to Bob's office building, but it's okay. Doesn't need to, just needs to know how to get it to the next hop. So think of, instead of a physical birthday card, computers send packets. And so you take this birthday card, and it is basically packets are basic transports of digital communications. So it's a sequence of ones and zeros, and they all contain a source address and a destination address and body. So in the example, of an email, everything you do on the internet is done in packets. Every web page, every picture, everything you send arrives in a series of packets or is delivered to you in a series of packets. So how does that compare? So you've got your envelope and card, got your sender's address and your destination address, the birthday card's in the envelope. Well, it's like that with a packet. There's a header, which is kind of like the envelope. It contains the sender's IP address, the recipient's IP address, and then the payload is the actual data you're sending. So in this case, the birthday card. So that's great, but how does it get where it's going? And there's this technology called packet switching. And it's basically a mode of transmission where the message is broken into little bitty bits, and they're sent one at a time, independently over the best route possible. And then they're reassembled at the end, at the destination. So again, buy a birthday card for Bob, cut it up into little bitty pieces. You put each piece in an envelope with Bob's address as the destination, yours as a source. All those little pieces take the most direct path possible, and they're reassembled in order at their destination. And then Bob gets his birthday card or email or whatever it is you're sending. So each step, again, has limited knowledge, but each step knows how to get to its next destination, making it one hop at a time. So let's take another example. Say you've got your buddy in Japan, you're in San Francisco, and you want to send this picture, this 1 megabyte picture to Japan. Or there's 8 bits in a byte. So this picture has 8 million bits that need to be sent. So the likelihood that information is going to get messed up on the way is pretty high. So if you tried to send this whole image in just one big go, you're going to lose something. And then you would have to start all over and retransmit it again and again. So instead, take the picture, split it into smaller pieces. And, the biggest piece is going to be like 1,500 bytes. That's basically the limit on an Ethernet packet. And then you can, if there's any problem with any one part, it just retransmits that part. The other end says, hey, I'm missing this sequence, and they resend it and everything's good. So why packet switching? It's efficient and it's cost effective. And most of all, it's scalable. So back in the day, and I remember these days, if you wanted to transmit data, you had to have a dedicated line between 2 points. So you would have to call up the phone company and you would get this line, and you would, be able to send things to each other. But the line just sat there unused when you weren't sending anything. So that's not very expensive. And these lines were extremely expensive. So with packet switching, data packets find their destination without the use of a dedicated channel. So you can throw all this data into one big pipe. The pipe can be shared, and all the packet needs is the address and a few protocols to push it along the way to get it where it's going. So it's really this whole internet model, the TCP/IP layer protocol stack model, which we actually cover in detail in Networking 201. But for the purposes of this course, we'll skip this part. So that's great. So that's basically how things get around the internet. So let's look at how it applies to the home network. So take Alice again. Alice lives at 614 Spring Drive. She has a lot of IoT devices. She's got her printer, game controller, her phone. She's got a wireless network. And, the APs probably plug into at least one of them plugs into the switch. She might have a TV, or a laptop that plugs in directly. She's got this great home automation system. She's got the fridge, the camera, the water features, all this stuff. Maybe the control panel plugs directly into the switch. She's got a great TV setup. And so home theater and AV media controller plugs into the switch. Everything that can plug into the switch does. Then everything from the switch plugs into the router. Router plugs into the modem, out to the internet. So all devices are connected to the switch. The switch is connected to the router. So as you can see, the entire network rides on the router. So as we talked about, computers communicate in packets, and packets need addresses. So there's two types of addresses. Every computer or device on the internet has two addresses. They have an IP address, which is a unique unique address assigned to every device that's connected. And then there's the MAC ID, and that's a unique physical address that identifies a device. Like my iPhone has a unique MAC ID, and all the numbers mean something special in the sequence. So a network packet needs both addresses to get to its destination. But the router uses the IP address and both of them to send it to a particular device on a LAN. We're not going to really talk about MAC IDs too much. We can talk about those in other modules. We're going to focus on IP addresses for now. So back to her cool home automation system. This is how Alice sees her network. She sees her game controller. She sees all the things. This is how Alice's router sees the network. Totally different. So everything communicates in IP addresses or network addresses of some sort. So enter the IPv4 address, the basic structure of an IP address. So in the case of an IPv4 address, you've got 4 sets of 3 decimal numbers. And there's 2 parts. There's the network address and there's a host address. And we're not going to get into things like subnet masks and stuff, but that tells you like where the network address is and where the host address is. But in this case, the the stuff that you're going to run into the most in the networks are having the first three sets are the network address, and the last set of digits is the host address. So every network has a unique network address, and every device on that network has a unique host address. So again, the network address is the IP address identifies every device connected. And so because of these network address schemes, it allows the internet to scale. So in this case, her house may have a 192.168.2 network address, which is a lot like the street number and the street address of Bob's office building. And then the host address, the thing for the individual device, is a lot like the suite number. You get into the building and then you can find the exact street. So it's a lot like when you park at the airport, you have to remember to take a picture of your parking space. It's like you can have different parking lots that you can park on. Maybe I'm going to park in the green lot or the orange lot or long-term parking. And then that green lot, let's say it's, in the analogy, the network address is 192.168.2. The orange lot is 192.168.1, and long-term parking is 192.168.3. But each individual space within the lot has a unique number. So that's like the host address. So if you say, I'm going to park in the orange lot in space 31, it's like saying you're at 192.168.1.31. So without the host number, the host address, you can imagine chaos would ensue, because imagine you're you're at Cedia and you're in the hotel and you order pizza, and the pizza guy gets to the hotel, which is at the address 192.168.2, but without room numbers, he has no idea where to deliver the pizza. So room numbers in this case are the host address. So you may have heard of IPv6. So IPv4 has 4 sets of up to 3 decimal numbers. IPv6 has 8 sets of 4. So this is one honking big number, and you'll see these, but like I said, in most of your installations, you're going to see IPv4 addresses. And that's what we're going to talk in terms of this course. But why did they come up with IPv6 anyway? Well, back in the day, with the combination that you could get from 4 sets of 3, it was like 4.3 billion possible addresses. And it's like, what could possibly go wrong? This is great. We have plenty. But I'm looking at probably 5 devices on my desk right now. So immediately it was starting to become clear that the sharp growth and, the security concerns that, oh my gosh, we're going to run out of IPv4 addresses. So enter IPv6, which gives you 340 undecillion, whatever that is, addresses. So there's no shortage any longer of worrying about IP address, running out, but they're not universal yet. You'll see them here and there, but not always. So in terms of these IP addresses, there's also this notion of there's public addresses and private addresses. So they can be public, which means they're reachable on the internet. It's something that is facing the internet. Everybody can see it. And then there's private, not reachable on the internet. So those are like your home networks behind your routers. So why? Well, again, part of it was we were running out of IPv4 addresses. So we had to have a way, with all the bunch of devices people were starting to accumulate in their homes and offices. It's like, okay, we're gonna put a public facing IP address on the router that's issued from the ISP, but then we're gonna translate that into a private IP address that only we can see. So it makes makes it secure, because these devices can't find my TV from the internet. It's hidden behind my private IP address. But it also conserved the IP addresses that were running out quickly. So that begs the question, how do resources on the internet find their way to you if you have a private IP address and they can't see you? So enter network address translation. So NAT was developed to conserve IP addresses. Like we said, not every device in a home would need a public address. They were running out quickly. So this is great. And it also is a privacy thing. It hides your network from the rest of the world. So while private addresses keep you hidden, without NAT, no one can find you or send you things. It's kind of like getting an envelope sent to you from an anonymous sender, and the sender expecting a response, but without a return address, there's no way to get one. So again, the way NAT works, since your home or businesses use private IP address, the router's starting to do a lot of work. It's translating the private IP address to a public address. It's sending the request out to the internet. You get the response, translate the address, and send it back. So what does that look like? Also, most home and SMB routers are NAT routers. So what does that look like? Here's Alice. She's at 192.168.2, and her laptop there has a host address of 10. She sends a request to the router, and the router translates her private 192.168.2.10 to its public-facing IP address, 203.10.113.12. She sends a request. It sends the request to YouTube, finds YouTube, YouTube responds. The router then takes that 203, that public-facing address it has, and translates it back to her device, and she gets her YouTube page. So that's great. So where does their network get all the private IP addresses anyway? So now enter the DHCP server. So here's this great protocol. So we know every device needs an IP address, and the DHCP's job is to assign an IP address to the host devices on the network. So that's great. A DHCP client sits on every host. The DHCP server is typically built into the router. And it assigns addresses dynamically. So what does that look like? It's like, let's just say that's her laptop. And the laptop over the DHCP client broadcasts to anyone who will listen on the network, hey, if you're the DHCP server, man, I need an IP address. And the DHCP server responds, well, I happen to have 192.168.2.30. How would you like that? And it's like, I would love that. So I'll take it. It's like, you can have it until 5 p.m. on Tuesday. And I'll check back with you like halfway through to make sure you don't need it longer than that. If you do, we'll extend what they call the lease. So every IP address has a lease period, and it's a great way to make sure that you use all your devices and IP addresses efficiently. So if you do need to renew the lease, that's great. You stick with the same IP address. But if your devices are turned off or unplugged or never used, no problem. You can just let the lease go, and the next time you need something, it'll come back. So DHCP, as you can imagine, is pretty cool. It's easy, it's automatic, and most of all, it's scalable. So you have this pool of IP addresses that you can just use all the time. But there are some devices that, especially in home automation environments, that it'd be really ideal if it had the same IP address all the time, like your media controller, like your, any controller that you use in your home theater system, and certainly some of the controllers like this. So a great option there is to use what they call DHCP reservations. It's basically saying, I'm going to assign you this so-called dynamic IP address, but I'm always reserving it for you. So it's still leased, but it's just ongoing lease, and it continually gives you the same IP address. That way, your different devices can find it reliably, It's really important in some of these control panels. It just makes life a lot easier. There's another option, an alternative to DHCP, which isn't used as much anymore. It's a static IP address. And as you can imagine, the name implies they don't change. And it used to be the way all IP addresses were assigned. And it didn't take long to realize, oh my gosh, this could be a mess. It's time consuming to configure and track them. They have to be manually assigned by the user network administrator. You often ran into like, oh my gosh, I have a duplicate address. And if you change anything in the network, you have to manually change the IP address. And as the number of devices increased, so did the headaches. So this would be my worst nightmare. I would be terrible at IP addresses, static ones. So they're used in some situations, but most network installers prefer DHCP reservations. So let's do a quick review from what we've learned so far. Every device has a unique address. The address can be either public or private. NAT translates the private address, that private IP address, to a public IP address so people can find us. The DHCP server doles out private addresses like hotcakes from its pool so that everybody has a private IP address as they need it. And then some addresses need to be fixed. So you can do that with DHCP reservations or a static IP address. So how does all that work if Alice wants to, now that we know how her local network works, let's go back to this YouTube thing. So how does she get to YouTube? So protocols make things move around the network and the internet. And protocols are basically rules that everything follows so that everything gets to where it's going in an orderly fashion. NAT, DHCP are just two of the protocols used inside the local area network. And then you'll hear terms like HTTPS, SMTP, usually from email, DNS are a few of the protocols used on the internet. So again, Alice goes to YouTube. What's involved in making that happen? Well, let's think about everything you see on the web. Web pages are written in HTML. They use HTTP and HTTPS almost universally now as the protocol that sends and helps them send and receive information. So Alice wants to go to YouTube. Her computer sends a request using HTTPS to youtube.com. YouTube receives the request. YouTube sends the web page back using HTTPS, and then she gets her web page. But wait, how exactly does her computer find YouTube? How does she know YouTube's address? So enter the domain name system, DNS. You've heard this probably a billion times. So that's the fact that what's helpful here is humans think in terms of names. We think in terms of youtube.com. Computers think in terms of numbers. Names don't change. IP addresses can change. And also, like, who wants to memorize their favorite site IP addresses? That would be terrible. So it's kind of like the old days where you had a phone book. And you looked in the phone book you remember your friend's name, but you couldn't necessarily remember their phone number or their address. So you could look it up in the phone book. So DNS is really the phone book for the internet. It's the protocol that turns domain names into IP addresses and allows browsers to find websites and other internet resources. So when you type the URL youtube.com into the browser, the DNS query, there's a DNS query that automatically takes place and sees what unique IP address is associated with youtube.com. So the first thing it's going to do is look locally in your browser cache, like Firefox, see if you've ever been there before. If you haven't, then you need the phone book, or if it's been a while, then you need the phone book. And the DNS server through a bunch of steps, resolves the requested domain name and translates it into its current IP address. So when you think about it, DNS, I'm pretty sure it's the biggest database in the world. It handles billions and billions and billions of requests in fractions of a second. And you've got these DNS servers located all around the planet. And it's a pretty sophisticated little system. So now the circle is complete. Alice wants to go to YouTube, and using NAT, the router converts Alice's private IP address, 192.168.2.10, that's assigned by the DHCP server to the router's public address, let's just say 203.10.113.12, then does a DNS lookup on YouTube and sends that request to YouTube's IP address. Request goes over HTTPS. YouTube says, got it. And it's going to send that request back over HTTPS to the public address it has for Alice's network. The router receives YouTube.com page at its public address. Using NAT, it translates it back to its private network address, the 192.168.2. It finds Alice's host address and sends it to the private IP address that belongs to Alice. And voila, she gets her web page on her screen on her laptop. So congratulations. That is essentially how things move around the internet. So a couple more ideas, and then we'll take a minute to see if there's any questions in the chat. Quick word on other networking terms that you may hear. VPNs, virtual private networks. And it's not what we're talking about when you're wanting to watch the soccer game and you get one of those little services to pretend you're in Spain. This is like when you are connecting a vacation home to a main home, or an office to a home, or multiple offices together, or maybe an employee or parent needs to connect back home while they're traveling. Basically, a VPN creates a secure tunnel between two networks. And they have a public key and a private key. And so basically they're exchanging secrets. And once the secured connection's been established, data can flow securely, privately. It's one of my buddies used to say, it's like taking a long, long Ethernet cable from your office building and connecting it to your home. So we talk about a lot more about these kind of terms in Networking 201. And then you'll hear the term VLAN, virtual local networks, local area networks. And that is a collection of sometimes disparate devices that need to talk to each other. So, or that you want to isolate. So perhaps a guest network. A guest network is basically a VLAN. So strangers don't have access to your home network. Or maybe you've got a bunch of offices around town, but you want to centralize the accounting function so that everybody shares the same printer for accounting that has the funny paper loaded in it. Or maybe you want all your security cameras on their own network. So it's basically a logical connection of computers and servers and other devices that are perhaps in different physical locations or have different purposes. And it's just efficient, it's often more secure, and it's a great way to leverage resources. So that's so far. Any questions in the chat before we keep going? If not, I will move on to the next section, which is networking components. So this is kind of the nuts and bolts of everything. So you walk into just about any network and you're going to see devices. You're going to probably see Wi-Fi access points or a mesh. You've got cabling that connect to a switch. You've got the switch that connects to the router, and the router connects to the modem or a gateway. And then you've got out to the internet. And so, the devices are link together to sort of form a network in a specific location. Radio waves on Wi-Fi connect the wireless devices together, lets them talk to each other. Cabling connects the wired devices together, and the switch, is like this big hub that lets these devices all talk to each other. Then you've got your router that forwards data between networks, and then you've got the modem that extends the internet service from the ISP. And then you've got that internet that's just this huge, vast network of computers and networks all over the world. But let's dig a little deeper into a few components. The switch is really kind of like the connector. The switch lets you connect all the Ethernet devices on the LAN so they can talk to each other. And the one thing switch uses Ethernet protocol for sending info, but it's only really good at sending info short distances, and it doesn't scale. It's a limited number of devices, and just you couldn't do millions and millions of devices on this protocol. So the switch is your connector, lets everything talk to each other on a local level. But the router is kind of the dispatcher. It's the internet protocol. Now that allows you to scale. And they act as dispatchers. They take the Ethernet signals coming in. They figure out the best route for where they're going based on their IP address. Then you've got the modem. The modem is really like a translator. The modem actually is short for modulator or demodulator. And it translates the digital signal from your network into an analog signal that your ISP can use, because analog signals can go far and wide, and they're very, very scalable. So reverse is true too. You're receiving something from the internet on an analog signal. The modem has to translate that, demodulate that, so that it can then go back and talk to everything on the network. So that's just a little digging a little bit more into those components. So let's start with cabling. I'm conscious of the time, so we're doing well. So cabling, there's all kinds of different Ethernet cabling you're going to run into on your network. Your coax, fiber optic, that has unlimited speed and distance. You've got your shielded twisted pair that you see quite a bit. You've got your patch panel connectors. So the main thing to think about with regard to cabling, Ethernet cabling, there's some things to pay attention to. There's the length of the cable. There's the shielding it has, the data rate, and where it will be installed. So the main thing that I always walk away with is Ethernet cables. They're designed to work on a maximum distance of 100 meters. So you want to stay within those parameters. Anything longer than 100 meters reduces performance. So bottom line on cabling, don't be out of spec. And I love this chart because it really does sort of show you how far we've come. Back, you've heard of, category 1 or Cat 1, Cat 5, Cat 6 cabling. Back in the day, like in the 80s, you could transmit 4 megabits per second over Cat 2 cabling. We're now at 100 megabits per second. Ethernet cabling on Cat 5, Cat 6 is 1 gig. You'll find that in commercial buildings as well. But I mean, you look at it and you go all the way up to Cat 8, my Lord, 25 gigabits per second over short distances. So, cabling, but the areas that you guys live is really that Cat 5, Cat 5e, and Cat 6 cabling. You've probably heard of PoE cabling. That is power over Ethernet. And it's designed so that you can get power over the Ethernet cable, so you don't have to run separate power supplies and worry about outlets. How many times have you tried to plug something in and it's like there's no outlet close? So it's low voltage. It's time and cost savings are great. You don't have electricians to worry about. You don't have to put in new outlets. It's low. It takes very little energy. It's very flexible. You can move things around, cameras, wireless access points, wherever you need it. It's very safe. and very, very reliable. And you can get UPS backups for in the event of power failure. And it's scalable. You can install and distribute this pretty simply and effectively. So then you've got switches. So again, we talked about a switch. It connects multiple devices on the network together to create a network so the devices can talk to each other. And there's two types. There's the unmanaged and there's the managed. And you can imagine they differ in capabilities, security, and cost. So just a quick overview of the managed versus unmanaged switches. Unmanaged, it's basically like a hub. It's almost like a power supply that the little power strips, you plug things in and you can share this power. This is the same way. You can plug devices into an unmanaged switch. They don't really do anything except it does let them see each other. There's no security typically. They're inexpensive. They're very easy to use. However, managed switches, they can be finely tuned. You can allow certain devices to talk to each other. You can manage specific down to the specific port if you'd like. They provide security settings that protect the network, gives you a lot more control over how data travels and who can access the data. And as you can imagine, they're more expensive. They're harder to provision and manage. They usually require a higher level of expertise, and which is, of course, added cost for staff and skills. So that's essentially the difference between those two. Wi-Fi, got the Wi-Fi part of it. Wi-Fi, it's basically a family of wireless protocols. You've heard of the 802.11 IEEE family of standards, and it's usually used for local area network, connecting devices to the internet over radio waves. There's a ton of versions. And they range in everything from interference and compatibility. And you've heard of Wi-Fi 7 is coming. The standards have not been ratified yet, but the word on the street is it's very, very fast. And sometimes I think the Wi-Fi 7 actually rivals a lot of the wired speeds that you'll get from your internet provider. You've got greater channel bandwidth. So not only is it faster, but this is almost like a 3D kind of image thing. It's like going from a 2-lane road to a 4-lane road. You can just dump a lot more data on there. And then the data density is like 20% higher. So just all in all, it gives you so much more speed, capacity. And like I said, is on Wi-Fi 7 can rival some of the speed and capacity you get on wired routers, wired protocols. So you've heard of access points, APs, and then you've heard of mesh systems. So they differ a little bit. Access points you can place around the house, and they create a wireless local area network. But they're wired to the switch. An access point is typically wired to the switch, and it then projects Wi-Fi signal to a specific area. A mesh is very convenient. It is usually just one node of the mesh is connected to the switch, and all the others are wireless, and so they don't have to be connected. And they're great for covering large multi-floor houses and that sort of thing. Mesh systems, though, the great thing about mesh is it's super easy to install. You hook your one node to a switch or a router, you place the other nodes around, you plug them into power, they find each other. It's really easy to scale. But unfortunately, because they are talking to each other wirelessly in the other rooms, they're typically a little bit slower. And so you may see delay in performance. So in a lot of high-end installations, they like to use the APs versus the mesh. And then we've got modems and internet service speeds. So you get your internet connection, your ISP, when you order service, you're either going to give you a standalone modem, in which case you'll need a separate router and APs and mesh, or they're going to give you this modem router Wi-Fi combo. We call it an all-in-one, but it has what you need. But then you can use your own router if you'd like. It requires some configuration. The trouble with these all-in-one devices, they're typically not enterprise grade. They're usually the most cost-effective thing the provider can find. They're not necessarily up to date. In fact, they're frequently out of date and not necessarily up to the latest standards. So in some of these AV installations, you're not gonna see using the combo unit. You're gonna actually use your own dedicated router. And then there's the data plan. You choose the different speeds and services. You've got 100 megabits per second. So that's good for multiple users and devices. Anything 500 to a gig, you can basically do anything and multiple devices in high speed. So the faster the connection, typically the more you pay. So the one thing to keep in mind with regard to these internet connections. So just because you have multi-gig speed from your provider, oh, I got Google's 2.4 gigabits per second, it doesn't mean you're going to get multi-gig speeds on your network. Why is this? And it all comes back to the router. So it's kind of like, why is the Porsche faster than the Chevy Big Block, even though the Chevy engine's twice as big? It's because it's more efficient. The smaller high-speed, highly tuned engine is more efficient. Just because our engine's rated at 500 horsepower, by the time it does all its things, gets to the axle, to the transmission, to the wheels, you've cut out 50 horsepower already, probably more. And why is that? And it's because of resistance. In many routers on the network, they'll advertise multi-gig speeds. It's kind of like the quarter pounder. It's wait before cooking. By the time you add the resistance of VPNs and VLANs and all these devices and logging and filtering, intrusion detection, your multi-gig router puts out less than 1 gigabit per second. In fact, we put some things on a bench, and your 10 gigabit port is delivering around 300 megabits per second. It's crazy. So again, the more you turn up features, the slower things are going to do. And truly inexpensive, non-enterprise grade routers just don't have the efficiency to keep up. So what's the point of all this knowledge? It's basically, as we've said, your network rides on the router. So you really have to choose wisely. Home networks are basically what small business networks were of 2018. Home networks have gotten so sophisticated with all the IoT devices and the entertainment and all that stuff. So long gone are the days when you could go to Best Buy and pick up a Linksys, wireless router and everything's cool. You get all your printers and everything. But when you look at even the high-end routers, on paper, everything seems great. They tout their high port speeds, but then you bog down as soon as you turn up features. The updates often need hand-holding. They frequently need to be rebooted, which is never convenient. Sometimes there's add-on subscription fees for services you thought were included, and that drives up the price. Most, if not all, are built on open source code that creates lots of security risks, and they're complex to install, which erodes profit margins by the minute. So what we make is Island, and we sort of thought about the router a little differently. PerfTech comes from the enterprise and carrier world. Back when, when you're in the carrier space, you can't be down. You can't reboot the network. You have to have extremely high reliability. Our guys come back we go back to the earliest days of networking, where the guy who's 2 doors down from me invented the first commercial LAN protocol, ArtNet. We created the first LAN to internet connectivity box, which was the instant internet, which we were purchased by Nortel for that. And it became the best-selling VPN router, and then went on to the carrier space and created a high-speed router in there. And so we took basically all that capability, all that high-end capability, and we put it into Island, because the guys really wanted a home network, a home router that performed like they expected. So Island provides 2 million packets per second. That's just not raw throughput. That is with all features turned up. It's wired by design. It's not a wireless router. It's so you would have your access points or your mesh with it. It's 130,000 connections per second. When you look at a page like weather.com, it's not just the page itself. It's getting, I don't know if you've ever seen it, but it's getting ads, it's getting charts, it's getting all this stuff from all these different places. So you've got hundreds of objects that need to come together on a page very quickly. And routers bog down because they can only do a certain number of connections per second. We do 130,000 connections per second, which is crazy fast. We are not built on open source code. It's highly secure. It's the same code we've developed and used, when we were in Ford and Citibank and Chase and in all the carriers, 8 of the top 10 carriers. So that's the same code that drives Island. We support 5,000 devices. Actually, we support more, but we stopped counting. But some routers do have like 100 device limit. So that's something to watch out for as well. And the great thing is they baked in all the advanced speed features, so you don't need a PhD to install it. We did crack open an Arachnus just to see how it compared, because the guys are very particular about their hardware architecture. We use a quad-core 64-bit Intel processor. Arachnus will use a dual-core 880 megahertz. We use 4 gig of dual-channel error-correcting memory. We use 0.5 gig of single-channel 16-bit memory, 64 gig of flash storage, as opposed to 64 megabytes of flash. And other little things. We want internal power supplies. We don't like external power supplies. We're created and manufactured in the US. Most are made in China, and we have a 2-year product warranty, but mainly we have human stateside support. So all your calls, everything are going to be answered by a human and in the United States. So just as a summary, the way we see it, traditional router interfaces, they're exhausting. There's just so much tech speak out there. It's especially with regard to security, it just sows confusion. We have a long history of making hard technology easy. We bake everything you need into the router. It's pre-configured. It's automatic. You can adjust it if you'd like, but you don't have to. Everything is basically handled with a tap and a swipe. Seamless updates. You don't have to take the network down. And instant VPN setup. That's a really cool thing we could always show you. And it's basically all the features you'd expect in an enterprise or carrier grade router, but for the AV world. So with that, well, everybody have a great Tuesday.